Okay, so hey, here's the review. So we talk about the review and then we take the test after that. So if we look at the review, numbers 1 and 2 here, I would start uh, any scenario like this. I would start with the motion map because the motion map is going to tell you what's happening. It says the box below is being pushed and is motionless. It's being pushed, but it's motionless, which means you would draw a motion map that has no motion, that just dots, which means A is what? 0, which means the forces are what here? The forces, let me grab a text box here. Can I grab a text box? Where am I? Get me out of here. Text box. Oh boy. That is a large font right there. Holy mackerel. Oh my gosh. Whoa, 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 whoa. Oh gosh. What a nightmare. This is a struggle. And how about we change that to orange to match? So, balanced. How do we know? Because there's no acceleration. Has to be balanced. Now, scenario 2 here, let's just do both motion maps first. So the person pushes the shopping cart at a constant velocity through the store. Constant velocity. Constant length arrows, no acceleration, which means what here in terms of why does it reset itself? Oh my gosh. Oh. Balanced. Again, that one's balanced as well. How do we know? Because there's no acceleration. No acceleration, it's balanced. Okay, in both cases, which means our force diagrams have to show balance. Now, what forces are acting on the box? Force of gravity on the box. It's sitting on something, and you can see there the name of the force in the diagram. Force of ground on box or floor or whatever you said, table, like whatever you said it was, that's fine. Force of gravity on box, force of ground on box. Is there a force of the hand on the box? Yes, the hand is pushing on the box. Force of hand on box. Or finger. What direction? To the left. But it's not moving, it's motionless. So there must be what? There must be a friction force. They didn't tell us there was a friction force, but there has to be. There has to be a friction force. So again, we have force of gravity on box. We have force of ground on box. Those are balanced. We have force of the finger on the box pushing to the left. But we also have to have a friction force on the box to the right to balance out the force of the finger, or we don't have balanced forces. So again, we're using the fact that they told us it's motionless and that the forces are balanced, no acceleration, no change in motion. That means the diagram has to show balance. So we know there has to be something else besides just the force of the finger, even though they didn't say a word about friction in here. But the only thing that logically makes sense is that there is a friction force, because that's the only thing, since there's nothing else in the picture here, it's the only thing that would make sense that could be there. Now, on the other side, the cart. Oh, well, I guess we'll just look at the summations here. So the summation equations you were supposed to also write out. And so we have, since we have balanced forces up and down, we have balanced forces right and left, then everything we have is going to sum to 0. Force of gravity plus force of ground equals nothing. Force of finger plus force of friction equals nothing, because we have balance. Balance vertically, balance horizontally. Everything has to sum to nothing, 0, no net force. For this one, force diagram, we have, again, force of gravity on cart, force of ground on cart. They're balanced. The cart's not accelerating up or down. It's also not accelerating right or left. So is the person pushing the cart? Yes, it says person pushes the cart at a constant velocity through the store. Constant velocity. Constant velocity. So we have to have balance. Well, does it say anything in the statement about friction force? No, but it's the only thing that makes sense that could be there that's opposing the motion of the cart is the friction force that would possibly balance out the force of the person. So again, we have to, whether they tell us there's friction or not, we have to think through how to make it balanced. And there are some times where the presence of a friction force is the only thing that logically makes sense to make things balanced, if they're supposed to be balanced. Then you're supposed to write out the summation equations. And again, because they're balanced in both dimensions, they both have to sum to 0 as well. Force of gravity plus force of ground equals nothing. Force of friction plus force of person equals nothing. Now, someone this morning asked, does it matter which order we add them? Like in terms of in the summation? No. Remember, you can add one way or the other. So what's that called? There's a property. There's a property in math about that. I don't remember what it is. Anyway, that should be it. So again, motion map, showing the acceleration, force diagram with summation equations. Now, if we had numbers, we could put numbers in here. We don't have any numbers. We don't put numbers in. Now, next question. Explain each of Newton's 3 laws of motion. Well, the first one. Objects that are experiencing balanced forces will not what? Will not have a change in motion. They won't speed up. They won't slow down. They won't change directions. They will have no change in motion whatsoever if the forces are balanced. If the forces are unbalanced, then there will be a change in motion. You'll have an object speeding up or slowing down or changing directions. All 3 of those things would be a change in motion, right? So balanced forces, you can't change directions, you can't speed up, you can't slow down. Unbalanced forces, you have to speed up, slow down, or change directions. Have to. There has to be something about your motion that changes if there are unbalanced forces. That's the first law. Second law is the F equals ma one. The force, unbalanced force equals mass times acceleration. Maybe I can do a, oh my gosh, it reset it again. Why won't this thing stay put? I want it to stay put. Unbalanced force equals m times a. Now, with this, oh my gosh, it changed it again. So unbalanced force equals mass times acceleration. That means if the force gets bigger, your acceleration gets bigger. I mean, come on. If you push something harder, it's going to accelerate faster. If you push with less force, it's going to accelerate slower. That's if the object stays the same mass. If the object's mass changes, if you have 2 different objects, both experiencing the same force, let's think about this. Let's consider this. If I have a softball, and I'm going to grab this softball, and I'm going to throw this softball as hard as I possibly can, with all my might, as maximum of a force as I can muster, and that ball is going to accelerate while I'm pushing it. Now, once it leaves my hand, then it has whatever velocity it has, and it's going to go however far it's going to go. All right. Now, if I change this out from a softball to maybe a shot, like a shot put, If I change this out to a shot, maybe it's 12 pounds. A 12-pound shot versus a softball. They're about the same size. If I try to throw that shot, that 12-pound shot, with as much force as I just threw the softball, is the acceleration going to be as big? No. So, same force, way more massive shot, increased mass is going to cause a decrease in acceleration. Okay? So remember, the acceleration does the same thing as the force. If the force gets bigger, acceleration gets bigger. If the mass, though, gets bigger, acceleration gets smaller. The more mass of the object with equal force didn't change. If the object gets more massive, then the acceleration is going to get smaller. Remember, they do the opposite. However, if I take from a softball, if I move down to like maybe a tennis ball, something less massive than a softball, then I could make it accelerate even faster because it's less massive. Less mass means accelerate bigger. I hope that makes sense. That's the second law. Third law, remember, that is the action-reaction, that every force has a pair. If you punch the wall, your fist hits the wall hits your fist. How do those compare? Equal amounts, opposite in direction. The wall will only hit back as hard as you hit it. That's Newton's third law, okay? Now, the problem with the third law is that you start getting confused about when there's movement involved. I think most of us, like if you think about hitting the hammer or hitting a wall with a hammer, and the hammer hits the wall and the wall hits the hammer, most of us are probably okay with, well, yeah, okay. The hammer does to the wall what the wall does back to the hammer, equal amounts, opposite direction. That's called a force pair. Remember, it's called a force pair. That we had that the other day. We wrote down that that's what Newton's third law is about, that there is a force pair, that every force is part of a force pair. They're all equal in size, opposite in direction, but they're not in the same system, like the foot and the ball situation. Let's see. Where was I? So for the third law, when the things are stationary, it seems to make more sense. But when I do throw the softball, I exert a force on the ball. The ball exerts a force back on me. How does the force on hand, or force of hand on ball, compare to the force of ball on hand? Force of hand on ball, force of ball on hand. How do those compare as I throw the ball? They are equal amounts, opposite direction. They're in completely different systems. Their names are reciprocals. The agent and the object flip. Force of hand on ball, force of ball on hand. Third law says that they have to be the same. My hand experiences the same amount of force as the ball does, but in opposite directions. That's just the way it is. Now, this is the one that's probably the most confusing, though. I'm going to bring this up. I brought this up in class. Force of gravity. Is there a pair to Earth's force of gravity on you? Earth's force of gravity on you. Is there a pair? Why doesn't this change? Why can't I just... So is there Earth's... I can't put an apostrophe in? Earth gravity force on you versus your gravity force on the Earth. Oh my gosh. So these two forces right here, Earth gravity force on you, your gravity force on the Earth. Are those a force pair? Yes, because we've just switched around the agent and the object, which means they're equal. Newton's third law says that those two forces are equal in amount, opposite in direction. You are pulling on the Earth as hard as the Earth is pulling on you. That one's hard to accept. But folks, the mass of the Earth, this is the mass of the Earth. How much effect do you think you're 150 or 200 or 120 or whatever, however many pounds you weigh, do you think that force is going to affect the Earth very much? No. It is not going to affect the force. It's not going to affect the Earth very much. The acceleration of the Earth is going to be unmeasurable because the mass of the Earth is so big. You're pulling on the Earth as hard as the Earth is pulling on you. Now, here's the proof. This right here, and you don't have to know anything about this, but I'm going to show it to you because this is the truth. If you want to figure out how much force gravity, Earth's gravity is on you, you take this equation, which includes in the equation both the mass of the Earth and the mass of me. My mass times the Earth mass times this thing, a big G, it's just a number, divided by this D squared thing, that is the force of gravity on me. Or I should say, the force of gravity between me and the Earth. That means it's the force of gravity of the Earth on me, and it's the force of gravity of me on the Earth. We're both in the equation. My mass is in the equation. Earth's mass is in the equation. You can flip them around if you want and say that it's the Earth on me or that it's me on the Earth. You can flip those around if you want. But it's the same calculation, which means the force of gravity from me onto the Earth is exactly the same as the force of gravity from the Earth on to me. That's bizarre, but it's the truth. Okay? The Earth and I are doing the same thing to each other gravitationally. It's just that my mass is so small that my acceleration is huge. So when I fall, the Earth doesn't fall up to me. I fall down to the Earth because my acceleration is huge because my mass is so small. The Earth's mass is so gigantic, it doesn't budge. I mean, it technically does, but it's so small, you can't even measure it. So we just say it doesn't move, it just stays there. All right, that's enough of that. We got to keep moving here. So next question. If you are pushing on the tailgate of a pickup truck on a hill, but the truck continues to accelerate down the hill, what can you say about the forces on the pickup truck? So here you are. Truck on the hill, you're pushing up on the truck. Truck is sliding down the hill, accelerating as it goes. Your feet are sliding. You're getting pushed down the hill. What can you say about the forces on the truck? I hope you're saying that the forces on the truck are unbalanced. Unbalanced forces on the truck. How do you know? What does it say? The truck is accelerating down the hill. The forces on the truck have to be unbalanced. They have to be unbalanced because it's accelerating. Next question. Is the pickup truck pushing you with more force, or are you pushing the pickup truck with more force? Which one's pushing whom more? In other words, there's a force of pickup on you and a force of you on pickup. How do they compare? Refer to the conversation we just had about Newton's third law. Which one's greater? Neither. That's a force pair. The truck can't do anything more to you than what you do to the truck. Now, are you both accelerating? Yes, you are both accelerating down the hill. So you both have unbalanced forces, but you're both doing the same thing to each other. Okay? You're accelerating down the hill because what the truck is doing to you is enough to make you accelerate down the hill. What you're doing to the truck is not enough to keep gravity from pulling the truck down the hill. So the forces on the truck are still unbalanced. The forces on you are unbalanced because the force of the truck on you is more than the force of friction against you. And so you're going to keep sliding down the hill, accelerating down the hill. But that does not change the fact that what you do to the truck does back to you. No more, no less. Same thing, because that's the third law. And again, many of you can quote it, but you don't really believe that it's true. If you did not say that those two forces are equal, then you do not believe the third law. I hope you believe it by the time you take the test. Number 5, if a go-car has a constant force acting on it, what will it do? Go-car with a constant force on it, what will it do? Now, most people, when they hear that the go-car has a constant force, well, they say, well, it's going to move with a constant velocity. Let's see if I can I show the go-car? Oh, look at that, right there it is. So everybody, here's the deal. If I take my force probe that we had before, if I take my force probe here, and I push on the go-car like this with a bent card, and I continue to push and push and push, constant push, a constant push. What is this go-car going to do? It's going to get faster and faster and faster. As long as I'm pushing with this card, it's going to get faster and faster and faster. I mean, draw a force diagram for it. What forces do we have? We have a force of, oh no, I need a pen. We have a force of gravity down on the car. We have let me draw a dot. We have a force of table up on the car. And then to the right, we have a force of card. We have a force of card on car. Is that balanced or unbalanced? It's unbalanced, which means the car is going to speed up. As long as that card is pushing, it's going to speed up. Because we've said that, remember, these wheels are so good here. We say it's pretty well frictionless, okay? It's pretty well frictionless, this car. So we don't put a friction force on here because, again, it's so small, we can just ignore it. It's as though it's not there at all. Now, what happens the moment I stop pushing? As soon as that constant force is gone, so as soon as I've changed its motion by pushing it with the card, causing an unbalanced force, as soon as I stop pushing it, what does it do? As soon as I stop accelerating it, it travels with a what? Constant velocity. Why? Because once I remove the force of the card on the car, what does the diagram look like? What does the diagram now look like? Now it's balanced. Now it's balanced. Once I remove the imbalance, there's no more unbalanced force. There's no more change in motion. The go-kart continues to move with a constant velocity. Now, you saw this in class. The problem is, though, in your gut, when you see that there's a constant force, you think that that means constant velocity. But it doesn't. It means constant acceleration, a constant change in motion. I hope you remember this. Now, in terms of this, page 2 here. I'm just going to kind of fly through this, and then you can see what happened. Here's what we did. We took a summation here. There are two forces to the right, a 2 Newton and a 4 Newton. They're both to the right, so they're both positive. Those get added up in a force summation, and that's going to equal MA. How do we know it's MA? Because it's unbalanced. There's nothing pushing over here to the left. So everything's pushing to the right, nothing to the left. So we say, well, yeah, that's unbalanced. So that equals MA. Now the net force, that's the sum. What's the sum of 2 newtons plus 4 newtons? It's 6 newtons to the right. So the answer, again, for the net force is 6 newtons to the right. Then the next question is, what's the acceleration? Well, that means I got to plug my 2 kilogram mass into where the M is and then isolate the A. I got to get the A by itself. So then I'm going to divide both sides by the 2 kilograms to get it over to the other side. And 6 over 2 is 3. And a Newton per kilogram is the same thing as a meter per second squared. And so that's why my answer is positive 3 meters per second squared, or 3 meters per second squared to the right, we would say. Now, letter C here, I've got 5 newtons to the right. That's positive 5 newtons. I have 5 newtons to the left. That's negative 5 newtons. What's positive 5 plus negative 5? Nothing. That's balanced, right? Balanced means we don't have a net force, which means we don't have an acceleration. Easy enough. B. We have 8 to the left. That's negative. We have 10 to the right. 10 to the right, 8 to the left. What's the sum? Well, we know it's going to be MA because they're not balanced, right? They don't balance out. So it's not going to be equal to 0. It's going to be equal to MA. And how much net force is there? Well, we've got 2 more to the right than we do to the left. So that's a net force to the right of 2 newtons. Then to find the acceleration, we got to put 4 kilograms in for the M. I put 4 kilograms in for my mass, divide both sides by 4 kilograms. 4 kilograms goes away on this side. I have 2 newtons over 4 kilograms. That's 2 over 4, which is 0.5. That's a half, right? And you can, again, it's either newtons per kilogram or it's meter per second squared. E. What we got here? So E, we have negative 5 newtons here because it's to the left. We have negative 2 newtons here because that's to the left. But then we have positive 10 newtons because that's to the right. So we have 2 different forces to the left, both of them negative, and then we have 10 to the right, which is positive. What's the sum of all of that? 3 newtons to the right. That's the net force. The end result of having 5 to the left and 2 to the left and then 10 to the right is the end result is that we get 3 newtons worth of force to the right. That's the net force. Then you got to put your half a kilogram in there, 0.5 kilograms in for the mass. Divide both sides by 0.5 kilograms. Divide by 0.5 kilograms. 3 divided by 0.5 is 6. And so we have 6 meters per second squared as our acceleration. And this one. Oh, this is the same as the C. Why even bother? We have 5 newtons to the left. That's negative 5. We have 5 newtons to the right. That's positive 5. Hey, that's balanced. And so a negative 5 plus 5 is nothing, which means this thing has no net force, which means it has no acceleration or no change in motion. And then lastly, we have this one. What's going on here? Oh boy, I got the whole mess in here. I got the whole problem. You can see the whole thing all at once. We have 90 newtons down. We have 10 newtons up. That is negative 90, yeah, positive 10. Negative 90, positive 10. Negative 90, positive 10, plus positive 10 equals MA. Clearly it's unbalanced, right? Clearly unbalanced. So it's got to be equal to MA, not 0. I add those together, I get negative 80 newtons. So that means my net force is 80 newtons down because it's negative. Then I put my 15 kilograms in for my M, divide both sides by 15 kilograms to get the A by itself, divide by 15 kilograms here, which gives me a negative, again, because there's a negative sign there, gives me a negative 5.3 meters per second squared, or newtons per kilogram, or meters per second for every second you pick. So that's the kind of stuff you need to be able to do for the test. Hopefully you'll go back and study and make sure you know the laws, and not just that you know them, but you believe them. Make sure you can, write out force diagrams, that you can put motion maps in place, that you can write out summation equations. I mean, all the stuff we've been practicing, it's all going to be on there. If you have any questions, you can let me know. Otherwise, I will see you later. Take care of yourself.